is Colton Sleister, and today I'm going to talk to you about the research that I've been doing in Dr. Marofsol's organic chemistry lab over the past 4 semesters here at Drake University. Specifically, the project I've been working on is using, it's looking at N-alkyl methylimidazolium ionic liquids in terms of the synthesis of them, their use as an oxidation reaction solvent, and then all of those things being combined into a short, easy undergraduate organic chemistry lab experiment. So, the purpose of this is to, like I said, it's to design an undergraduate teaching lab for organic chemistry. In this teaching lab, the students will synthesize an ionic liquid, and then they're going to use that ionic liquid as a solvent for oxidation reaction, specifically the oxidation using hypochlorite ion as the oxidizing agent to oxidize an alcohol into a ketone or an aldehyde. And so what this will show students, it'll teach them about green chemistry, green chemistry being chemistry that's more environmentally friendly, things that are reusable or recyclable, things that are not super volatile are categorized as being green, things that are non-toxic are green. And unfortunately, a lot of organic chemistry happens in solvents that are not green. It might use toxic or dangerous, strong oxidizing agents, or it could also be done in solvents such as benzene, ethyl acetate, toluene, that are really not good for people that are volatile. Get into the air, you have to do it under a fume hood, so it's just inherently more hazardous, and we'd like to reduce that in teaching labs. In addition, it will teach students about, by having them use it and hopefully understand why they're using it, it'll teach them about SN2 nucleophilic attack and anion exchange reactions, so double displacement with ionic compounds in synthesis, and then the oxidation chemistry of alcohols to ketones. And I won't show up, but there's a mechanism for that they would be understanding is going on. Also, they will be using TLC, IR, and NMR as the analytical methods to monitor these reactions as they're taking place. And very importantly, this must be done. You have to be able to do this cheaply because it's a teaching lab, and you have to be able to do it quickly because you maybe have 3 or 4 hours that you can actually do one lab section. So the reason that we're synthesizing the ionic liquid in the first place is that they're very expensive, prohibitively so. It might cost for 25 grams, small amount. You can get it from Sigma Aldrich. For 25 grams, it might cost you $200 to $500, so it's way too expensive to give a ton of it out to students. So what we're going to do instead is have them synthesize it from cheaper starting materials. Now, what an ionic liquid is, it's basically a molten salt. Salts, sodium chloride, classic example of an ionic compound. Sodium chloride melts at 800 degrees Celsius, so you can't use it as a solvent for anything. It's a solid. However, if you change the anion, change the cation, make them bigger, kind of spread the charge out, that ionic attraction gets weaker, decreases the lattice energy, and you get something that's a liquid at room temperature. It's viscous, but it's a liquid. So in our case, we're using BMIM, butyl methylmidazolium, BF4, tetrafluoroborate, and that melts at negative 80 degrees Celsius. So it's very liquid at room temperature. In addition, although they have a low melting point, they're much more thermally stable. They're much less volatile than traditional organic solvents such as benzene or ethyl acetate because it's a salt. So that's one of the attractions to them as a solvent system, as a green solvent in the first place. Also, it's been reported that they're recyclable. Things in the Marofsol lab have shown that they're recyclable, and you can also customize them by changing the anion, by changing the cation. You can get a large number of different ionic liquids that might have that might solubilize differently. Some of them actually act as catalysts, so we have a range of them that we can do, which is attractive when you're trying to optimize the conditions to be done quickly and with undergrads. In addition, just so you know, these ionic liquids they're good for things other than teaching and writing papers. You can there's been research that shows that they have applications in industry, such as fuel purification, that they have applications in pharmaceuticals, so it's definitely recently it's a hot topic in chemistry, and so I think teaching students about that is pretty cool. So here I have, just to show you all, I'm not making this up, these are two salts, sodium chloride, and a BMEM ionic liquid. This is both at room temperature. This is a liquid, it's a molten salt. This is a salt, it's like solid, like you would kind of expect when you think of ionic compounds in the Gen Chem context. So, the oxidation reaction that we're going to be doing has been previously characterized by Dr. Marusel in the late 90s. We use, it's actually a phase transfer reagent catalyzed oxidation reaction. It's actually fairly green because it uses sodium hypochlorite, which is bleach. That's the active ingredient in bleach. It uses that as the oxidizing agent, so it's not too harmful. It does it at room temperature, and it uses ethyl acetate and as a solvent for the organic portion of the oxidation. When you do this in reality, you can read what's going on here. When you do this in reality, you have two phases. You have the aqueous phase, and then the ethyl acetate is its own organic phase, and that will contain, for example, the 9-hydroxyfluorine that you might be oxidizing. And so in order to get our oxidizing agent into the organic phase so that it can oxidize, we have to use a phase transfer catalyst, which in this paper it was tetrabutyl ammonium bromide. It's a tetrabutyl ammonium, so it can kind of ionically bond. It has an electrostatic attraction to the hypochlorite ion, and then it also has some hydrophobic portions which allow it to go into the ethyl acetate, and then by doing that it can transfers things from one phase, the aqueous phase, into another phase, the organic phase, and you can do the oxidation reaction. However, this is still done in ethyl acetate, which is not the friendliest solvent. It's not terrible, but it is volatile. Just so that you've seen it, this is what BMBF4, I'm going to say that abbreviation, for 1-butyl-3-methyl imidazolium. This is the imidazole ring, imidazolium meaning it's charged, and then BF4, tetrafluoroborate, is its anion. At this point, I'm going to, if anyone has any questions, I can answer those. I'm going to talk more about what we've actually done, but if you have any questions over the background, I can hopefully clear those up so the rest of the presentation makes sense. Okay, now I'm going to describe the literature, a little bit more background, but this is very, very relevant about what we're doing in the lab right now. Some more slides about ionic liquid synthesis and oxidation reactions in ionic liquids. So, like I mentioned, we have to synthesize the ionic liquid ourselves because it's too expensive to buy from Sigma Aldrich. It's very well reported that you can combine 1-methylimidazole with 1-bromobutane, and then if you have some source of energy, whether that's a microwave, reflux, sauna bath, you get BMBR just by a very, very simple, very textbook SN2 substitution. However, BMBR is not, for oxidation reactions, it's not a very good ionic liquid because the hypochlorite we found actually will react with BMM Br. It reacts violently and does not. You end up not oxidizing anything, but just kind of destroying your ionic liquid, which is not what we're trying to do. So, what I'm going to show over the next few slides is that it's been reported, like every part of what we're trying to do, the synthesis, the anion exchange, and then the oxidation in anionic liquid has been reported in time and under the time constraints that we were looking at, except for one step. And so our hope is that by optimizing that one step, we can have something that we can synthesize these different papers, have a single protocol for undergraduate lab experiments. That would be something that would be useful, publishable, and pretty cool. So, this first thing that I'm going to show you is the same oxidation reaction that Dr. Marofsel and the tetrahedron letters had reported. About 10 years later, a group in China, they showed this done in ionic liquids, and they tested a lot of ionic liquids, and they found that BMNBF6 is a good solvent. They also tested the KPF6 and I think an acetate analog of BMM, but they didn't work nearly as well for oxidation. And they showed that it's done in 15 minutes. You just add the sodium hypochlorite, exactly the same conditions that we'd be using with ethyl acetate, just it's not phase transfer catalyzed, and it uses a much greener solvent, BMNBF4. And the alcohol, it's generally it's benzyl alcohol or some relative of benzyl alcohol. So there's some variety of alcohols that we can use in our experiment. Like I said, this has found BMNBF4 to be the optimal ionic liquid for a variety of benzyl alcohol species oxidation. This is important, and because they've already optimized the oxidation reaction with different ionic liquids, with different alcohols in those ionic liquids, we don't need to focus on that in our research. Instead, we can focus on synthesizing those ionic liquids, because in this paper, they just bought them, they bought their ionic liquids from some commercial source, which is maybe feasible in research, but not in teaching. So, then we look at some papers. This is from 2013 in the Journal of Chemical Education, and they have taken some reported procedures for making BMM PF6, different than, not the right ionic liquid, but it's related. And they showed, like we showed, that you can just use neat conditions. So you just add methylimidazole, you add bromobutane, you reflux it for 20 minutes, and all of the SN2 has gone to completion. And then you have BMNBR, and then under aqueous conditions, you can turn that into, just by adding the potassium hexafluorophosphate, you can turn that into a PF6 ionic liquid, which is great if, but unfortunately, like the paper of Rong et al., the Chinese group, and even we've verified this in our research, that ionic liquid is not so good for oxidation reaction. Maybe it would be useful for Diels-Alder condensation reaction or something like that, but not what we're doing. This is what I just said. So we found another paper. Fun fact, this is from the Arabian Journal of Chemistry. So it's a kind of I think a Saudi Arabian group did this work. They have a much slower way of synthesizing BMNBF4. It took them, they refluxed in acetone, even though Journal of Chemistry Education shows that you can just do it neat. They did that for the SN2, but what's really important from this paper, is that they converted BMNBR, they added NaBF4, just the sodium salt of tetrafluoroborate. They did that in acetone with stirring. Took them 10 hours, which we can't do. Cannot take 10 hours, and they did it at 40 degrees Celsius, and that gave them BMBF4, which is exactly what we want. So, what we're trying to do is we're going to take the first step of BMMBR synthesis via SN2 from the Journal of Chemistry Education. We're then going to follow that up with an optimized, a yet to be optimized version of the anion exchange from the Arabian group. And then we're going to use Rong et al.'s oxidation reaction in that ionic liquid. And with those things, that would be our a protocol for an undergraduate experiment. The main thing that we need to work on right now, that's what I'm doing this week, is we need to shorten the 10-hour anion exchange step from that last paper I showed you. Because we don't have 10 hours, so maybe if we increase the heat, that would help. We might play with the solvent that they used, or we could try it in aqueous conditions, and we need to find some way for that to occur faster. Like I said, I've been doing this research for a while, and although the slides that I've just shown you look very succinct, like just look this up in the research and then you know exactly what to do, it was a bit of a winding path to get here. Because initially we were trying to oxidize 9-hydroxyfluorine in the ionic liquid. Like I mentioned, our first ionic liquid was actually it reacted with our oxidizing agent, so we had to change that. We also tried to change the polarity of our ionic liquid by changing BMIM to OMIM, so changing a butyl tail into an octyl tail. And we hoped that would dissolve 9-hydroxyfluorine better. However, we then found that the hypochlorite ion is not always available in ionic liquids. And about that time, that's when we looked and found that there was that research had already been done, that Rong et al. Had optimized those conditions, admittedly for not the alcohol we were hoping. We were hoping to use 9-hydroxyfluorine, but benzyl alcohol should work as well. So then once we had that, we decided to focus on optimizing the ionic liquid synthesis steps, and that's what we've been doing since then. So in the future, like I said, we have to do the anion exchange faster, and once we've done that, I think that's doable. Once we've done that, we will assess the ease of that oxidation reaction, and monitoring the synthesis, monitoring the oxidation reaction in an undergrad setting, so with TLC, with IR, with possibly NMR. And then once we've figured out that this is actually doable for undergrads, we'll integrate the 3 steps, we'll make a protocol, and then hopefully we can publish that in the Journal of Chemistry Education. Thanks for your attention, and at this point I can answer any questions that you might have.